so let's see how we go. I can make it longer or shorter. We'll see how we go, and Sean will let me know if it's going over time.
Yep.
So today I'm going to talk about my career, mostly mine, very subjective, because I am in a water industry and I'm in the consulting environment, so it's a very narrow view. Nevertheless, it's an experience, so you take what you can. You don't have to take everything, and there'll be a lot more broader aspects in career as a chemical engineer, in construction or operations or in other fields like oil and gas and chemicals, etc. But I'll give you a glimpse of what it's like in the water industry. So I'll go through a little bit of me, and then give you a bit of a context around how the water system works in Sydney, and present you with some issues and challenges, and hopefully that kind of distilled to what we meant to be as a chemical engineers, and give you a little bit of what our chemical engineers do in Jacobs in the water industry again, and I'll give you a few kind of a practical things that we produce as a chemical engineer, and we'll give you a bit of a career project highlights, if you like, that I've gone through over the past 20 years, and then I'll answer any questions. So, a little bit of me. I was born in Korea. I graduated to Australia during high school. Married happily. I have 2 children. Hannah, she's finishing her HSC today, and Sammy is 12, and he's going to high school next year. So I did engineering, environmental engineering, during my undergrad, and I was asked to, there was an opportunity to do a PhD after that, so transfer over to chemical engineering, and I did research on the membrane projects. I started my career in a company called Sinclair Knight Mertz. It used to be an Australian company, and in 2001, and later it was bought by my current company, which is Jacobs, and Jacobs is a US-based consultancy. About 10 years ago, and through my career I've kind of employed as a graduate process engineer, and worked through my ranks, and I became a team leader, and I was kind of testing the waters a little bit as to whether I should pursue technical career or management career. So I was just testing water at the time for about 10 years. That's a long time, but anyway, I did that, and then I decided to maybe I should be a technical person, and I became a technical director of ANZ. So that's kind of a little history of mine, and the picture here is my family, my team when I was team lead, and it was shot from one of the conference. I think it was IDA. Sean hosted that here. So a little bit of context, issues and challenges for water industry. So there have been various challenges along the way. In the 80s and 90s, a lot of it was driven by pollutions. So back then there was a lot of pollution in the beach, like Bondi and Malabar, etc., where the sewage was directly discharged to the ocean, to near shore outfall. So every now and then there is a big storm event or something, then the fecal coliforms in the water, so those beaches were very good, and it was clearly visible from naked eyes. So at that time, Sydney Water and the government decided to put a deep ocean outfall, which will take a few kilometers into the ocean and discharge it in a far instantly that cleared out the pollution. So that was a fairly milestone thing for the water industry at the time. And also there was a lot of nutrients in the inland system where algae and so on start to affect the ecosystem around the inland rivers. And often the algae growth and vegetation growth in the river was so great, it looked like a land where you could walk on, where in fact it was a river. So again, a lot of capital investment was made to make sure the treatment is done right and clean up that process. So now we have a lot better waterways. In the 2000, there was significant growth with Olympic Games and so on. So a lot of it was to making sure all the facilities are up to date and accommodating the growth. And also there has been a lot of environmental regulation tightening. So again, not only have to amplify the systems, but also have to make sure we can treat to a better standard. When it comes to now, it's beginning to be a problem of resilience and adaptation with the climate change and also the variabilities that we are seeing. So the current key challenges are how do we make sure that we have enough water system. So when we're again the dam, our biggest dam in Sydney was built in the 60s. We thought we had enough water for everybody forever. That was the thought at the time. But we eventually catched up, and the rainfall, which I'll show you a chart a little bit later, is dwindling so much that we are at a point of not having enough water to provide a long-term average flow. So that's one of the key challenges. And also there is a drought. So I don't know whether you were around, but in the 2000 there was a big drought. And more recently, not many people realize it, but between 2017 and 20, there was a fairly pronounced drought that made a lot of water authorities and government worried, which I will show you a picture a little bit later on as well. And over time, the raw water quality coming into the water filtration plant has been deteriorating, and also there's a bit of likely changes in the Australian water, the drinking water guideline as well. On top of that, there's other drivers like carbon neutrality, the sustainability. Customers are more aware of things happening, more stakeholders, indigenous people wanting more water, and social equity issues around water is rising, and that all, I guess, that all are compounded with all the issues and challenges that we faced in the previous decades. So all of these. This chart shows a bit of a supply and demand of Sydney. So the shaded area is the future of the water demands that we are anticipating. So the future is not clear. There is a scenario that we have a huge population growth versus small population growth. That's why it's showing kind of wide shaded area. The line represents the most likely case that we are anticipating. And as you can see here, we are already over in terms of exceeding the supply at the moment by about 44 billion a year, which is equivalent to about 150 megs a day. Any idea of the scale? 150 megs a day. Some people call it 150 swimming pools a day as a scale, and yeah, and it's likely that the gap will increase because of all the growth that's happening, and also the climate isn't getting any better. So we're going to see more intense rainfalls and prolonged drought. So that all kind of counting effect, and ultimately, or by 2060, will be around 250 million shorts. In terms of long-term inflow trends, so that's the amount of water going into our dams. If you have a look at the overall average for the past 100 years, the average flow per year is about 1,400 gigaliters a year. But if you just look at the last 30 years, that drops to about half. So whilst it is a historical record, the future may be even more bleak than what it is currently. So that's a long-term trend and average. If you have a look at the last drought, this is showing 2 cycles of the last 2 droughts. So this one over here, sorry. This one over here is showing the depletion trajectories of the storage dams during the last millennium drought, and the slope indicates how severe the drought was. So we think the millennium, most of us think the last millennium drought was pretty bad. More recent one, about 10 years later, we had a lot more severe drought, but it only lived for about 2.5 years. Then we had a huge rainfall in one day, and the drought was broken instantly, which was a lucky case. But what we are seeing is this type of severe drought is happening again and again, and also the intensity is getting worse as we use more water with the population growth. So something to be mindful. Just going on with the drought again. So this is the curve that I constructed if we didn't have any water coming into the dams. So if you add all the dam levels in Sydney, and if you see the demands and how much we take out, this would be the curve that the dam will experience over time. If I overlay what the last drought has happened over that 2.5 years, it almost followed exactly the same pathway, which means we didn't have any net inflow to the dam. And that one day, where that big rain came and ran off straight off. So that was lucky. But at the time, the plan for Sydney was to build a second part of the desalination plant. So we have one that is currently operating. Sydney were planning to build another one if the dam storage was hitting 35%, so that's at that time. But the construction period that will take is such that if the drought continued, we would have passed the point of zero, past the point of where we don't have any water coverage. So it was very, very, very close, and this plan had to be updated. So alternative to that, we thought this was one of the studies that we did, is, if that's the case, what can you do? So we were following, so this dotted line is the current trajectory with the asset portfolios that we have. And if we were to have another 500 megs a day of rainfall and supply, this will follow these trends. So it's almost like flattening the curve a little bit. But what it essentially gives us is that when the dam level hits 50%, it does give us enough time to respond to it. So it was one, I guess, mitigation measures that we can put in place that will negate or mitigate the long-term effects of the long-term drought. So yeah, that was a thought. Now, in terms of the water quality has been deteriorating over time, and we're not really sure why. Some people think that after we constructed the dam, the stuff sitting in the dam floor has been rotting all this time and started to release all these organic chemicals. I don't know, Sean, you might be able to have a better view of this, but you know, all these organic matters started to rot and release from the dam floor and starting to impact the water quality coming out, because it's consistently getting worse and worse. So this is a color. Color is one of the surrogate measures for the organic content in the water. When one of our biggest treatment plant was designed, it was designed with the level that is shown here. And over the years, the color or organic content has gone up and up and up and up. So what that means is the plant was designed with a lot better quality water at the time. That means with the water deteriorating, the plant will not be able to produce as much water as what was initially intended. So that is an issue. So what does that mean? Well, for us as a chemical process engineers, and any other water practitioner for that matter, we need to improve our system resilience. That means we need to better manage the water resources that we have. We need to do something about the demand so that we don't use or waste too much water. And also, for the existing facilities, we need to make sure that it's robust enough so that it can sustain whatever the nature decides to throw at it. Something that I haven't covered is that Sydney's water system is very isolated, so there's not much connection between them. So there needs to be a better interconnections, and also we need more climate independent water supply, like a desal plant or recycling plant. And their efficiency has to be improved, because we all signed up a piece of paper which says we're going to become carbon neutral by 2050. And there will be more water demand in the future. Sydney's growth is mainly happening in the west, where it's a lot more drier, therefore we need a lot more water, and there's no more water coming out from the west, because our dams are all in the west, but the storages are dwindling. There are more demands for water though, like environmental people want more water, the indigenous community want more water, and there are some disruptive technologies like hydrogen requires more water, data centers requires more water. So there is all this water that is needed as we go into the future, but the supply is not necessarily matching up with that. So, and finally, there are emerging contaminants. The technical advances now enable us to detect things that are in a very minuscule concentration in the water, but now we have the instruments to determine what it is and possible cause of it. So as we know more, we need to get a lot more, therefore more things to be done. So that's kind of a homework for every water, I guess, professionals, and as a chemical engineers, there are things that we will be a part of the solution. Any questions so far? Give you a bit of a context around. It's really because the developments has been happening in isolation, if you like. So when there's a town and there's a dam, it just makes the dam to the town. It was sufficient for providing that.
The small population.
Yeah. And then we started to grow and so on. It's all kind of pockets of various communities attached to a single water filtration plant and a dam, and that was enough.
So is that why, like, I think it was during the last drought, Sydney wanted water from Southern Highlands Dam, and Southern Highlands wouldn't allow it or something?
Yeah. It's a political battle. So Sydney's water system is primarily serviced by Warragamba Dam, which is Wollondilly River, but it also has connection to Shoalhaven River. So these two rivers has very similar flow, but the Shoalhaven River has very small storage. So in the time of drought, what happens is they can pump a lot of that water to Sydney to support Sydney system. So there's a problem there, because when there's a drought, if both system dries up, then Shoalhaven people say, why are you taking our water? But at the end, Sydney has 5 million people, Shoalhaven has 100,000 people. See who's going to win that battle. So, but that water is very expensive too, because to pump that much water from Shoalhaven to Warragamba, you've got to lift about 400 meters. So normally you don't do that because it costs too much. But in a time of drought and when the dam levels dropping down like crazy, that is something that has to happen. And you can expect, city like Sydney, 5 million people, you can't let it dry either. So that's a dilemma, and so by the way, during the last drought, both rivers decided to dry up. So normally we have either one or the other getting dry. Last time both got dried up, and that was what worried the government so much at the time, because we have contingencies, right? So we have one river we primarily depend on, and the other is a backup. But both the primary and the backup, that was a big concern. And it's got to do something. Yeah, it's got to be a way to get climate change in the life.
You can't just hike it everywhere, right? It's expensive.
No, water is very heavy. It costs a lot to transfer from one to the other. It's not like fiber optic cables where it's thin and long, whatever. But it does cost a lot, to do that. So anyhow. Okay. So chemical engineers. I can only talk about Jacobs because this is a company that I've been with since I graduated. So I only work for this company. So I can only tell you about what's happening with Jacobs, right? So in the water infrastructure section, which is where I belong, we have about 80 engineers. So consist of process, mechanical, civil, not structural, electrical engineers, and the planners, modelers, etc. So we've got about 80 people, and of that, we have 20 process engineers, and they are mostly chemical engineers. So if you count the sum, that's not the number of people, proportional number of people in chemical engineering. So what we normally, we do various work, so it's not really, one good thing about working in a consultancy is that every project is slightly different. So you'll do a project one day and the next day it's going to be different, most likely. So that's a good thing, the variety, but then again, you know, Jacobs does very similar things to the GHD, you know, they do similar things to Workcon and Acon. So yeah, that's the reality. Now, in terms of process engineering, we get to do a fair number of things on a technical side. So pre-feasibility studies and feasibility studies of the water facilities, the reference and concept design, and the business case support. Because what normally happens is, if government wants to say, you know, if we need a desalination plant here, then what we need to do is we need to do enough engineering to come up with a cost so that we can provide a business case to the government and say, well, Mr. Government, to build a desal plant will cost you $2 billion. Do you want to go ahead? So that's something that we do very often, and it's not just chemical engineers, but whole suite of different engineers. But we do play a very critical role of what it is. When they decide to build something, say Sydney Water wants to build a wastewater plant, for example, normally they go out to a tender. So to deliver a facility, that will require us at a consultancy like us or design firm with our contractors, the ones who build the thing together, form a partnership, and we design and they build. But before they are selected as a successful party to carry that out, the contracting party will have to come up with a cost. So this will cost you $20 billion, $2 million, whatever, to the body, and they'll have to be selected to carry on. So we do a tender, that's called tender design, and it's a certain percentage of the overall design, so that allows very competent pricing, because once the pricing is set, that is sealed. So unless there is a very good reason, the company will have to deliver it within that month, essentially. And there's a detailed design which go into a lot more detail and go through every individual items within the plant and commissioning. So commissioning is actually, once it is built, we make sure that whatever process unit is functioning as per its specifications. And apparently that's a lot of fun. Actually go to the field and you know, touch things and you know, do a walkie-talkie with the operator and say, well, turn this pump on, you know, and see what's going on. And that's when you actually see what you design and build. So people do get a lot of pleasure out of doing that, and that's a lot of achievement. That's really kind of building things, but also we do a lot of troubleshooting. So if a certain plant doesn't work properly, we dig into the problem and see what we can do. And also every now and then, the owner of the asset often need to do a, check on whether their plant is performing to its intent, and do a process capacity assessment. That's what it's called. And earlier on I said, you know, we do a lot of planning as well. So planning and strategic advices that we give out to Sydney Water and also other government authorities. And I would say I do about half of my time doing that, and maybe half of my time doing some design. So that is very large part of us doing. So we're not necessarily kind of calculating and doing things, designing things all the time. We do other things too. So, role of a chemical or process engineer in a typical design project. Chemical engineers are typically in a process group, and process engineering takes place at the very early point. So if you think about a big water plant, process engineers are the first one to go in and make sure things are all kind of according to what the design has to meet. So we're responsible for setting the design parameters, like what's the feed characteristics and what is the target water quality that we need to get. What are the preferred, or identify and select the preferred treatment process, or are we going to use membrane, are you going to use the deep bed filters, those type of things we need to do, and that's a lot of fun doing that. And also we prepare the basis of design. So we will say, well, here's the water coming in, this is how much is coming in. You need to produce this quality water at that amount, and we're going to have this much waste going out, and individual characteristics is this, and we're going to use this type of process units, and that's our basis for our design. So that's done very early, and there are other engineers who work on it as well. Not everything in that basis design is belonging to us, but we do a lot of it upfront. And so that's where it starts. And then once that is set up, then we do a lot of calculations and modelings to come up with a solution. And we start to put drawings together. And the two key pieces of drawing for chemical engineers are called process flow diagrams, which I'll show you in a minute, and process and instrumentation diagrams. So they are the two drawing deliverables that the chemical engineers take ownership of. In a detailed design phase, we write functional description describing what the function of each individual process is, and control philosophy, how it is controlled. So turn this pump on, open this valve, wait for feeding head, turn this off, those type of things. And then after design is all complete, we write a part of the design report, and the process engineers write certain section, mechanical design, structural design, etc., and then that are pulled together. Now, as a process engineer, we tend to interact the most with others because, first of all, we are at the front end, and that's where we need to liaise with the clients about and workshop together, come up with the process units and various other design decisions. And also we need to talk to the guys in the mechanical team, the electrical team, the hydraulics team, and so on, because we set out what is needed at the beginning. So we do a lot of coordination. So the process flow diagrams looks like this. It looks very simple diagrams with the boxes and lines and whatnot. But behind that, there's a lot of calculations. So every line will have various parameters set up. So what are the flows? What are the typical concentration of key chemicals? Pressure. Whether it's an intermittent or continuous line. Every line will have that kind of information in it, and these are put together typically by chemical and process engineers at the very beginning. And it normally comes with a table which describes individual lines. So this is what the stream is and all the information that goes with it. So this is a desalination plant PFD. So the second piece of drawing that I mentioned is process and instrumentation diagram. So there are hundreds of these diagrams in a typical large plant, and they represent every lines, every pipelines, every equipment, instrument, valve, you name it, in it. So this is where other disciplinary people will take information out from. So mechanical people will have to come up with every one of these mechanical unit item and start to describe what they are, so that someone can go up and buy them, and also put together what it's going to be look like. I mean, it doesn't look anything like what's on the ground, but this is fundamental in laying out mechanical units and structural units and so on. So this is a very, very fundamental, I guess, information, and a lot of other information will be drawn from this. Also, this will have a rough size of everything, so if there is a tank, then they'll say, well, we need a tank of 50 kiloliters or whatever. So, yeah, it's got various information, and a lot of it can derive from this. So, you don't want to get this one wrong, because it has very many ripple effect downstream. These days, people use what we call Smart Pen ID. So once you draw it, it automatically produces a database behind, so that it can tag everything with all the information for it. So, for example, a line here will say, well, what's the size, what's the material, yeah, etc., etc. Those information will be automatically captured, and that's the fun thing about Smart Pen ID, because in the end, remember that there will be hundreds of these drawings. Counting all the valves in these drawings could not, it's not fun counting all of them. They're all different in shapes and sizes and so on. So having a database like that is of great help. So just yeah, so it's a Smart Pen IDs, and when it's laid down, it used to be a fancy thing, but nowadays it's pretty common. Even every client wants a 3D modeling of it, and nowadays people call this 3D modeling. So 3D model, you know how it's kind of 3D. There's 4D drawing, which tells you the construction sequence, or it will tell you build this one, and so on. And 5D is during the operation, and 6D when it's decommissioned. So there is a lot of more dimension to it than just visualization, but you can do a lot of things on top of that. So 3D model is quite common, and what we do these days is, instead of drawing the 2D drawings, which the constructor will need to have in order to build a thing, what can be done is we can section it out, just cut a section, and it can draw the 2D drawing straight away, rather than having to draw it manually. So once you have model built, and you can cut various sections, that becomes a drawing. So it's a great visualization tool, and is widely used for communicating with stakeholders and the clients, and also do a lot of analysis, so that often what you see in 2D drawings, the plans and sections, can't, unless you have a very spatially well-oriented person, can't really see whether pipes going through a wall will be on here or there, and so on. So with the 3D model, you can just can visualize that easily. So it can be a very good tool for crash detections, and also whether a person can fit through a certain hole. For example, it's a great invention, and I have a very, very poor geospatial orientation. So someone like me, brilliant tool, man, I couldn't figure it out. So it's a very, very good tool, and it becomes very common. So I mentioned earlier, we do get involved in something other than typical design, like strategic advices and the plannings, and I think, I mean, this is my personal view, but process engineers tend to do those things a lot more than others because we tend to see things at a higher level. So and we do communicate with multiple parties, different disciplines and clients and the stakeholders. That makes us a little bit better strategically minded, so that we can see the bigger picture and so on. So we do a lot of planning. Nowadays the buzzword is adaptive planning. So the future is uncertain. We can't just make a concrete plan for the ultimate things that we want to be. But given that we have a very, very variable future, we need to be able to be adaptive to reach where we want to go. So that means we have all the options open and find a best pathway at a time. And if we think we are in a wrong trajectory, then we can turn around and be flexible and do something else. So various stages of planning that a lot of our process engineers end up doing, and that leads to a strategic advices for the government and other clients. And we do a lot of project management too. So project management is really about making sure the project is on time, on budget, right quality, and make sure people are happy. So we do a lot of project management, and along your course, I'm sure you will come across that subject. I mean, it is an art of itself, and there is a professional project management, but for smaller projects, some of us process engineers actually do the project management. So, some of the highlights. I've been working as a consultant for about 20 years. So, there's been various projects and different things that I've done during my time. And if I have to pick a few, I guess the one of the biggest project highlights for me is the Sydney Desalination Plant. That was constructed in 2008, 9, 10. It was the largest water infrastructure project since they built the Warragamba Dam. So it was a very large project, and project value at the time, 10 years ago, it was about $2 billion. So it was a very large project, and every time I fly into Sydney Airport, you can see it from the sky, and it just brings a smile to my face. So this is kind of an aerial view of what it is, and this is actually a 3D model that we constructed while we were designing it. So you can see the similarity between the two. Right? So this plant takes care of about 15% of Sydney's water need. But as the city grows, that proportion gets smaller and smaller, and there is a likelihood that this will double its capacity very soon. So that's very exciting. The next one, I was also doing, I mentioned I did a lot of planning work as well, so I was privileged to have been worked in developing the Greater Sydney Water Strategy last year. It's really looking at what the water future is going to be for Greater Sydney and make sure the future pathway achieves the resilience and security for water for the people of Greater Sydney. So this set out, how much rainfall intense capacity do we need to have, and what kind of infrastructure do you need to build over the time. Not necessarily telling what to do, but giving a guidance on what can come into play along the pathways. And over the next decade or so, some of this will materialize, I think. Because Sydney Water is already looking at some of these things, and having, so this is a strategy. So next level is planning. So Sydney Water is planning on a number of infrastructure that is consistent with this strategy. So again, I'm very happy that some of my work is going to be somewhere in Sydney. So that's a great thing to have. So others after Sydney. So since you've done one you do Greater Adelaide. So we've done similar things for Greater Adelaide, and we've done similar things for Greater Melbourne. Early on, during the last draft, I was involved in a thing called Greater Sydney Desalination Program. That was like an emergency. Crap, we're in trouble. Can we bring up a number of desalination plants to get over this drought? That was before the rain. So that was a great project. We did a very long-term plan for Water New South Wales, Greater Sydney Supply Augmentation Plan 2100. So that was looking at 80 years ahead. Some actual design projects, the Jolf desalination plant, because of the geography. So that one was at Northcote. So that was fun. Going there and have a look and so on. So that was great. I also was in various stages of design for a desal plant around Australia, so the Victorian desal plant and Adelaide, as well as some small stuff in Western Australia, etc. Earlier in my career, this thing called Metro Strategy for Recycled Water, and that actually was built later on. So this plant is at the St. Mary's wastewater treatment plant. It's an advanced water treatment plant, so it's producing a very, very good quality water from wastewater for the replacement of the dam release. So I think this is my last slide. So some of my suggestions for you guys. Communications is very important, both written and speaking, and also casual, because we do tend to write a lot, and we do present a lot as well. So communication is very important, and you should try to experiment, exercise, practice a lot. And also lateral learning is fairly important. You're not in your career, I don't think you're not going to be just doing a process calculation all your life, because that would be very boring to start with, but you will end up doing something else, right? So you will do a little bit of mechanical things, you might size different pumps or pipes or whatever. So, and also that helps you communicate with people in a different discipline which you will have to use as a process engineer. So lateral learning is a good thing. Chemistry is, I think I did tell this thing to others as well. Chemistry is, you are a chemical engineer, so be a good friend with the chemistry, because that's really a fundamental thing. Computer literacy is, well, I think you are already very computer literate, so a lot of things happening with digital twin, machine learning, AI, etc., and that started to make its way into process engineering as well. Work experience, of course, it's very valuable if you can, and you are in a pretty good hand, because there is this course has a work experience built in, right? So there we go. And networking, yeah, with friends and so on. So yeah, I think that's really it. So, questions?